Professor Sang-Hyun Kim for inviting me to speak here. It's always a pleasure to be here in Daejeon. So what I'd like to, so this first of these two lectures, I'd like to explain a right-angled Artin group action on a natural graph, all of these things I will define, called the extension graph associated to it, which mirrors the mapping class group action on the classical curve graph of a surface. So let me remind us what all these things mean. So gamma is a finite simplicial graph with a vertex set V and an edge set E. And then the right-angled Artin group is defined by the presentation so it's generated by the vertices of the graph, and two vertices commute if and only if they're adjacent in the graph. And then the extension graph, gamma E, is built out of, it can be built solely out of the data of the graph gamma, but it's a little bit easier to define it out of the data of the right-angled Artin group itself. This is the extension graph. The vertices of gamma E are given by conjugates v to the g, where v is in v and g is in a of gamma. So by this notation, I mean v to the g is g inverse vg, and the edges of gamma E are given by commutation so the vertices of the extension graph are naturally elements inside of the right-angled Artin group, and so we can ask if two such elements commute with each other, and if they do, then we declare them to be adjacent. So on the other side, we have the mapping class group. So here S is a orientable surface of finite type. So it has some finite genus and some number of punctures, both of which are finite. And then mod S is pi 0 of the group of orientation preserving homeomorphisms, or just the group of homeomorphisms of S up to isotopy. And now the curve graph is well, the extension graph is supposed to be an analog of the curve graph, which is yes.
What is commutator at the end there? What's the meaning of this commutator?
So if
how do you multiply vertices?
These are elements of the right-angled Artin group, and so I can compute their commutator within the right-angled Artin group.
They're elements of this V of gamma, right?
Yeah, but so V is an element of the vertex set, which is viewed as a set of generators for the right-angled Artin group. And so these are naturally elements of the right-angled Artin group.
So you have a generator and another element
Yes.
So it's here.
But I can, if I, by this is what the notation means. I'm actually looking at its conjugate within the right-angled Artin group.
So what happens if the treatment could be, for example, if you choose the V to Z instead of V to H?
Yeah, then they're equal in yes. So yeah, I'm considering these vertices up to these elements up to equality within the right-angled Artin group. Yes. And so these are elements of the group, and so I can take commutators of them. And if those commutators vanish, then the elements are adjacent to each other. And so then the classical curve complex, of which we consider just the one skeleton, is the following flag complex. The vertices are given by isotopy classes of simple closed curves. On S. So when I say a simple closed curve, I mean one which has no, it's a closed curve which has no self-intersections and which is homotopically non-trivial. And I also assume that in the case that S has some punctures, this curve is not parallel to a puncture, so it's represented in the case where S admits a finite volume complete hyperbolic metric, it's represented by a closed geodesic with no self-intersections. And then the adjacency is given by disjoint realization. So we said gamma 1 and gamma 2 are an edge of C of S if and only if gamma 1 and gamma 2 admit disjoint representatives. So if one represents curves by geodesics, then those are representatives of those curves which will be disjoint if and only if they admit, if and only if those particular representatives are disjoint. And so this graph requires a different definition in the case where the genus is low, or the number of, in the case that the genus is low and the number of punctures is also low. But I'm not going to get into that. So this will suffice for our discussion. And now the point is that the mapping class group acts on the curve graph by graph metric isometries. And so this is because an element of the mapping class group is a homotopy class of homeomorphisms, and homeomorphisms preserve simple closed curves which are essential and non-peripheral. And it preserves disjointness, and then a homotopy class of homeomorphisms will act on homotopy classes of curves. And similarly here, by the definition of the extension graph, we have an action of the right-angled Artin group on the extension graph by graph metric isometries. Okay, so now what I'd like to do is I'd like to give a perspective on some properties of right-angled Artin groups which mirror well-known facts about mapping class groups. So, unfortunately, we have to erase some of this. So there's a classical Nielsen-Thurston classification. In mod S. So this is formulated in some way by Nielsen and also then refined by later by Thurston. And the idea is that there are sort of canonical geometric representatives for elements of the mapping class group. So let psi be a non-entity mapping class. Then psi is either a finite order, infinite order and reducible, or pseudo-Anosov, and so I'll just briefly note a little bit in more detail what these three things are. So a mapping class has finite order if and only if psi is homotopic to an isometry of S. And here this is a slight lie. Here I'm assuming that S is of hyperbolic type. Because the torus admits isometries which act trivially on the fundamental group as autoautomorphisms of the fundamental group, but have infinite order. But this is sort of the most interesting case for dealing with finite order mapping classes. So psi is reducible if and only if psi preserves a non-empty multicurve. And so this is if and only if psi preserves a complete subgraph of the curve complex. So the original way that reducible mapping classes were defined by Nielsen was that there was some vertex of the curve graph. So there was some isotopic class of simple closed curves whose orbit was finite under iterations of psi. And then going from that one finite orbit to having an actual multicurve preserved by the mapping class is a highly non-trivial step, which was established by Bierman, Lubatsky, and McCarthy. And the third possibility is psi is pseudo-Anosov. If and only if psi, really it's some representative of psi preserves a pair of filling transverse measured foliations. Okay, so this is sort of how classically one thinks about the Nielsen-Thurston classification of mapping classes. So we can also sort of look at the action of the mapping class group on the curve graph and try and understand how one can formulate the Nielsen-Thurston classification in terms of the graph theoretic action of the mapping class group. And so that's fairly straightforward. So an element has finite order if and only if the psi action on the curve graph has finite order. And then an element has infinite order reducible if and only if psi has a finite and an infinite orbit in C of S. And psi is pseudo-Anosov if and only if each psi orbit is infinite. Okay, so now that's sort of what I'll say about the Nielsen-Thurston classification. And as I said, that the theme of the talk is to develop a theory for the right-angled Artin group which mirrors the mapping class group action on the curve graph. So one thing that we can try to do is to formulate a meaningful Nielsen-Thurston classification in the case of a right-angled Artin group. So to do that, we sort of need to develop a little bit more theory and make this sort of curve graph theoretic version of the Nielsen-Thurston classification a little more powerful. And the way to do that is through the notion of acylindricity. So it often happens that, well, in topology, when we have a group acting on a space, we always sort of hope that point stabilizers will be finite, or more generally that the action will be properly discontinuous, but in practice we often can't actually achieve that. If we have an infinite order reducible element, for instance, then psi has a finite order, a finite orbit, and that point, which so if we pass to some power of psi will fix some point inside of the curve graph. So every point in that orbit will be invariant under some power of psi, and since psi has infinite order, we see that points in the curve graph may have infinite point stabilizers. And so acylindricity is sort of manufactured to make actions with infinite point stabilizers, which are still relatively nice, into something that we can work with. So the setup for acylindricity is very general. So we have a group G, and it's acting on a metric space X by isometries. And what we're going to, so I'll give first the general statement of what it means for this action to be acylindrical, and then I'll give sort of an intuitive understanding. So the action is acylindrical if for each little r there exists a big R and a big N greater than 0, such that all pairs x and y in X with the distance between x and y at least r, we have that the number of elements of G such that the distance between x and G of x, y, G of y is less than or equal to r, is less than or equal to n. Okay, so let's unpack this definition a little bit. So what it's saying is that, if we can't say anything about the simultaneous. So the set of elements which move little x, say by a distance no more than little r, that's the little r quasi-stabilizer of x. And if 2 points are near to each other, we can't say anything about their simultaneous quasi-stabilizer. But what acylindricity says is that if we have 2 points which are really far apart from each other, they're really far apart with respect to the little r that we choose, then their little r quasi-stabilizers simultaneously are small and uniformly so in a way that doesn't depend on our choice of points. Okay, so that's sort of a hard to understand definition, but the use of it comes from this theorem of Bowditch, that says if x is a hyperbolic graph and gx on x by acylindrically, so implicitly by isometries, then each non-identity element is either elliptic, which means this is if and only if every G orbit is bounded, which is if and only if the stable translation length of G is 0, or it's loxodromic, which is if and only if every G orbit is unbounded, which happens if and only if the stable translation length of G is actually bounded away from 0 by a constant epsilon, which is independent of G. Okay, so if you have a group acting acylindrically on a hyperbolic graph, then you have these extremely strong possible conclusions, this very strong dichotomy about the possible dynamics of the group element actions on that graph. And so we're ready to review the Nielsen-Thurston classification now. So what Bowditch ended up proving, so I'm going to state two theorems as one. The first one is originally due to Mazur and Minsky, but also reproved by Bowditch. And the second one is due only to Bowditch. The first is that the curve graph is Gromov hyperbolic, and the second is that the action of the mapping class group on the curve graph is acylindrical. And so this very strong dichotomy immediately applies to the mapping class group. And so every element in the mapping class group now is either elliptic or loxodromic with respect to the action of the mapping class group on the curve graph. So the corollary that we can write to this is that if we have a non-trivial element of the mapping class group, then psi is elliptic if and only if psi is finite order or reducible, and loxodromic if and only if psi is pseudo-Nosov. Okay, so I clearly only made this entire setup if this was all the case for the right-angled Artin group acting on the extension graph, and that's indeed true.
What is stable translator max?
You want to define it? Oh yeah, okay. Yeah, sure. I had it in my mind to do it, but then I forgot. So, stable translation length. So you have a group acting on a metric space by isometries. And then if you have an element little g, then you can look at the distance between g to the n x and x. So here, little x is in big X. And so this is usually something that goes to infinity, so you can renormalize by n. And because these distances are subadditive by the triangle inequality, you can take the limit as n goes to infinity, and you should probably make this independent of the point which you chose. And this is defined to be the translation length, and this is always finite. Okay, so the theorem that was proved by Professor Kim and myself, one of the theorems, and indeed for the rest of the talk, any unattributed theorems will be due to Kim and myself. So in case I forget to write. We have that the A of gamma action on the extension graph. First I should make it parallel to this theorem. The first theorem is that the extension graph is delta hyperbolic. One should to be perfectly honest about this, if one considers the honest graph metric on the extension graph, one should assume that gamma is connected. In fact, gamma E is a quasi-tree. And the second fact is that the action of A of gamma on the extension graph is acylindrical. And so we can apply Bowditch's theorem about the dynamics of an acylindrical group action on a hyperbolic graph. And so an immediate corollary is that we get a Nielsen-Thurston classification. For elements of the Rightangled Artin group. Okay. So when we had the original Nielsen-Thurston classification in the mapping class group, we understood. The understanding of the Nielsen-Thurston classification via the action on the curve graph is just another facet of our understanding of mapping classes. And knowing that each element is either elliptic or loxodromic without having some other geometric intuition for what these mapping classes look like isn't very useful. And so that's the problem that we encounter now, is that we know that every element in the Rightangled Artin group is either elliptic when each orbit is bounded when it acts on the extension graph, or we know that it's loxodromic, so there's at least one unbounded orbit, therefore every orbit is unbounded. But without some sort of better understanding of what these elliptic and loxodromic elements are, this isn't terribly useful. And so why don't we give a better understanding of what elliptic and loxodromic elements might be. So I'll just state this as a theorem and then give some examples. So this is again Professor Kim and myself, is that if you take an element in the Rightangled Artin group, which we'll assume is cyclically reduced, and so what this means is that you write the word on a circle, and then if you are able to make any cancellations, you make them. And sort of take the shortest element in the representing G in its conjugacy class. And then we have that G is elliptic if and only if the support of G is contained in a join. So let me just explain briefly what this terminology means. So if we have an element, if G is just any element in A of gamma, then the support of G is the smallest subset of V, such that G is in the subgroup spanned by V0 and the cardinality is minimal. So you look at G as a word in the vertices of gamma, and you look at which vertices and their inverses occur. And just taking those vertices which occur in that expansion of gamma is defined to be the support.
So there are possibly many V0s.
Beg your pardon?
Several V0s.
So it's a non-trivial fact that this is actually well defined.
Yes.
Yes. So it is actually well defined. It's a good point. And then now what's a join? So if gamma is a graph, so we say gamma is a join if its complement is disconnected. So by the complement, I mean this is the complement in the complete graph on V of gamma. So to obtain the complement graph, you take gamma and you draw in all the edges which were not there, and then you delete all the edges which were in gamma originally, and gamma is adjoined if the resulting graph is disconnected. Equivalently, one can write gamma as a union of two graphs, gamma 1 and gamma 2, with V1, V2 spanning an edge of gamma whenever V1 is a vertex of gamma 1 and V2 is a vertex of gamma 2. From the point of view of right-angled Artin groups, joins are fairly easy to understand. So just as a matter of notation, when you have this decomposition, we'll often write gamma equals gamma 1 star gamma 2. So this is just saying that gamma decomposes the star of as the join of gamma 1 and gamma 2. So from the point of view of right-angled Artin groups, we have that A of gamma is equal to A of gamma 1 cross A of gamma 2 whenever gamma is gamma 1 star gamma 2. Okay, so what does this theorem say? So you start with this cyclically reduced element, and you look at the smallest sub-right-angled Artin group, which is induced by the vertices of the original graph in which that element lies. And if that right-angled Artin group decomposed as a direct product of two right-angled Artin groups, then the element was elliptic. And this is an if and only if characterization. So what this implies in particular is that if gamma is a non-trivial join, then A of gamma has no loxodromic elements. So let's consider some examples. For example, F2 cross F2, which is the right-angled Artin group on the square. So the square is a join of two proper subgraphs, namely pairs of opposite diagonal vertices. This is A of this graph star this graph, and this has no loxodromics. And what one can actually show is that, so I'll also call the square C4, it's a cycle on 4 vertices. One can show that C4E is bounded. And so you cannot have elements with arbitrarily large displacements, and in particular, you cannot have elements with positive translation length, stable translation length. Let's consider a different. It's not finite, it's infinite, but it's so
okay.
It has so yeah. So this is actually isomorphic to a complete bipartite graph on 2 infinite sets, and so it's infinite, but it has diameter 2. Let's consider the graph P4, which is just the path on 4 vertices. So the element, we can write down 3 elements, A, B, AC and AD. And now this element AB is supported on this graph, which consists of exactly two vertices, which is a join. And so this is elliptic. If we look at AC, that's supported on this graph, which has exactly two vertices, and they're not adjacent to each other, but one can see that this graph is actually contained in a subjoin, because the graph spanned by A, B, and C. So the graph here is path on three vertices, which is the join of this graph on two disjoint vertices with this one vertex. So this is elliptic. And then this guy is loxodromic because the distance between A and D is 3, and if A and D were supported in a join, then their distance would be at most 2. And so that's, and most, in some sense, I'll give a precise statement later, most elements that you write down inside of a right-angled Artin group will be loxodromic unless you really restrict your attention to a proper subgraph. So I'd like to understand what are purely loxodromic subgroups. So inside of the mapping class group, the only known purely loxodromic subgroups are virtually free. And in type-polar geometry, one wants to know various possible purely loxodromic subgroups. For example, this is an open question: is there a copy of the fundamental group of a closed surface of genus G, here G should be greater than or equal to 2, inside of mod S, where this S and this SG are possibly different, which is purely pseudo-Anosov. So the existence of such a group would have profound consequences in type-polar geometry. So this is at this point unknown, but great progress was made by Brian Bowditch. So he originally stated this theorem for closed surfaces, but it can be generalized to just one-ended, finitely presented subgroups. So I'm going to sort of not give a completely precise statement, but it'll be clear what I mean. So finitely presented one-ended purely pseudo-Anosov subgroups of mod S come in finitely many conjugacy classes per isomorphism type. So if you had an injective map from pi1 of S2, for instance, into the mapping class group of some surface, and the image were purely pseudo-Anosov, that would mean that there were finitely many copies of pi1 of S2 already sitting inside of the mapping class group. And your injective map, the image of your injective map was conjugate into one of those finitely many ones already. So in particular, finitely many can be 0. We don't know. Okay, so now one can pose a similar question for right-angled Artin groups. The conclusion is somewhat stronger only because right-angled Artin groups are a lot simpler than mapping class groups, at least in some ways. So let G inside of a right-angled Artin group be purely loxodromic. Then G is free. So here we don't have any finiteness assumptions on G. It doesn't have to be finitely generated even. And so all you assume is that every non-identity element inside of capital G is loxodromic. And the conclusion you get is that G is free. Okay. So I'd like to now mention another application of this sort of loxodromic elliptic dichotomy. So loxodromic or pseudo-Anosov elements and homomorphisms. So consider I'm just going to assume that I'll take SG for instance, where G is at least 3. Then what one can show is that the mapping class group of S has no center. So now let's take a normal subgroup of mod S. Then a theorem, a sort of surprising theorem of Ivanov, is that G contains a pseudo-Anosov element. Okay, so this seems sort of surprising at first glance, but one can sort of think about it a little bit, and it's not actually that surprising. So the idea of one way you could show something like this is that if you take any element psi in G and phi in the mapping class group, then the commutator of psi and phi lies in G, because the commutator is equal to psi conjugated by phi, which lies in G because it's normal, times psi inverse. And so then you can sort of think about Thurston's original construction of pseudo-Anosov elements. You suppose that, for instance, you have some curve here, gamma on your surface, and you assume that, say, T gamma is in G. And then you take, I'll keep the notation consistent, phi is some pseudo-Anosov. Then what you can do is you can consider T gamma conjugated by phi to the some big N. And so this is equal to the twist about phi to the N of gamma, which is going to be the twist about some curve which is completely going all over the place in this surface. And for most N, if you look at T phi to the N of gamma, T gamma inverse, this is again going to be pseudo-Anosov. And one can mimic this construction in general with reducible mapping classes. So you can always find pseudo-Anosov elements inside of normal subgroups. And this result has sort of a striking consequence about representation theory of mapping class groups. So let rho be a representation of mod S. And what I mean by representation, I just mean any action of the mapping class group on a set. I don't mean a linear representation. It could be a linear representation, but just anything that you possibly want. And suppose that rho restricted to some G, where G again is a normal subgroup of the mapping class group, is faithful. Then rho is actually faithful. So this again seems kind of striking, but the idea of the proof is again fairly straightforward if you look at it the right way. So let K, which is a normal subgroup of the mapping class group, be the kernel of rho. Then we know that there exists a pseudo-Anosov element inside of K if this is non-trivial. And now we also had an element, a non-trivial element of G, which is pseudo-Anosov and which is not in the kernel. So we have that there exists a phi in G, which is pseudo-Anosov. And so then what one can compute is that this commutator of psi and phi is not the identity. Furthermore, if I apply rho to this commutator and I get the identity, this, first of all, is in G. So when I apply rho to this, I do not get the identity. However, if I applied rho to psi and I got the identity, then rho would vanish on this commutator. And therefore, psi is not in the kernel. And therefore, the kernel of rho has no pseudo-Anosov elements in it, and therefore it has to be trivial. And
the commutator is
because so why is the commutator not the identity? That's because if you have two pseudo-Anosov elements, then they either share a common power or their commutator is not the identity, because sufficient powers of them actually generate a free group. Okay, so it turns out that similar facts hold for a right-angled Artin group. For certain right-angled Artin groups, one can see this fairly easily. I mean, sort of as a completely silly example, if you have a non-trivial normal subgroup, say NZ, sitting inside of Z, and you have a representation of Z map is just, I don't know, odd of some set, and when rho is restricted to NZ, it becomes faithful, then you have that rho is some infinite, it's a representation of Z which has infinite image, and therefore it has to be faithful. Similarly, if you had some normal subgroup of F2, then this same argument shows you that because any two elements in F2 either generate a cyclic group or don't commute with each other, that if rho is a representation of F2, which is faithful and restricted to H, then this implies that rho is faithful. And now, it happens that this fact is also true in general for right-angled Artin groups, although one has to state it a bit more carefully. For example, if I look at F2 cross F2, I can factor a representation of F2 via this projection map. And then I can take any representation here. So some out of any set S. By the way, I've said writing S for set here, I don't mean surface. So it's just some representation of a group. So if this was, say, projection onto the first factor, then this representation of F2 cross F2 is faithful and restricted to the first factor, which is a normal subgroup, but it's not a faithful representation of F2 cross F2. And so we have to state the theorem correctly. And so the theorem is actually that if gamma does not split as a non-trivial join, or equivalently, A of gamma has at least one loxodromic, and take a normal subgroup of A of gamma, then H contains a loxodromic. Furthermore, if rho is a representation of A of gamma and rho restricted to H is faithful, then rho is faithful. And I think this is probably a good place to stop for now. So.